We're going to continue our discussion on random variables that we started on our previous lecture, and we're going to start looking at how things might affect our random variables, both the mean, variance, and standard deviation. And the first thing we're going to deal with is we're going to continue our example from the Lucky Nook or the Quiet Nook restaurant, and use that same example that we did before. So all these examples will kind of circle back to that example from before. So if you haven't watched the first lecture, please you might want to do that now so you can make that, it'll make sense, right? But so let's just put here, for instance here, so we have, in addition to that, the Ace of Hearts special there, the Lucky Lover special, they add a $5 coupon in the local newspaper that will be added to any meal. Okay, so in addition to the game that they're playing with the cards, people might actually have an additional $5 onto their discount. And what would that do to the expected value and the standard deviation of the amount of their discount? Because that's what we're talking about. That's what that random variable represents, is the average amount of discount, right? So mean tends to behave like we think it's going to behave. So from the previous example, from the previous slide, I believe the expected value is $5.83. So if somebody comes in with a coupon for an additional $5 off, that will take the average and increase it by $5, right? So if you've got some constant that you're adding or subtracting to this variable, it will just add or subtract that amount to it. So in this case, we would look at it and it would add $5 to it. Variance-wise, and as a result, standard deviation-wise, it doesn't really add anything to it, right? This goes back to what we were talking when we first started talking about, rescaling data and adding or subtracting or shifting data back when we were first introducing mean and standard deviation, right? It's not going to make the data more spread out. It's just going to change where it is on where the distribution would lie, right? So the expected discount with the $5 coupon in play would be up to $10.83. The standard deviation, which was $8.62 before, is still $8.62, and the variance is whatever it would be. I can't recall what it was off the top of my head, but adding or subtracting doesn't change the variance. It only will change the expected value, and it'll change it by exactly the way you think it would change it. So one thing you could do is add or subtract a constant to that random variable. The other thing you could do is say, all right, well, let's say on Valentine's Day we go out with another couple, and when that is the case, when the two couples dine together on a single check, discounts are doubled, right? So instead of 20, 10, and 0, it's 40, 20, and 0. How will that affect the expected value and standard deviation of the discount? So in this case, what we're really doing is multiplying a constant to a random variable, or multiplying a random variable by a constant. I'm not sure why I worded it so awkwardly there. And again, the mean behaves just like you think it would behave. If your instinct is to say, well, if they're doubling the outcome, the average is going to be doubled, you're right. You're right. It is going to be doubled. You want to be really careful when it comes to variance, though. And this is where having an understanding of where the variance comes from, or where the standard deviation comes from, rather, would help you find, the correct variance. What it's going to do to the variance is not, in this case, double it, but multiply it by 4, right? So if we were to, multiplying a constant by a random variable by the constant, how it affects the variance is, all right, you're going to square that constant. So instead double it or triple it or whatever, you're going to square that. That's how it will affect the variance. So it will not double the variance, it will quadruple the variance. But then if we can keep that in mind, then the standard deviation is still going to be the same. We're still going to find it the same way. We're going to find the standard deviation from the variance. So our new expected value for the double the discount, and this is what's happening here. They're doubling the outcomes, right? They're doubling the outcomes. They're not getting two outcomes, they're doubling them, and they're changing the outcomes. And that will change the expected value from $5.83 to $11.66. Again, this is what on average, if everybody came in with these coupons, or if everybody was dining, with another couple, on average, that's how much of a discount they would expect to have to pay for all the people doing this. Standard deviation wise, now when it comes to the standard deviation, right, the variance would be now huge, right? Because the variance was, oh, there it is, $74.31 ish, right? So you're going to quadruple that. But standard deviation wise, we're still going to just be, it would still wind up just doubling the standard deviation. And if we needed the variance, which we oftentimes are going to need, don't just double the variance. If what you're doing is doubling the random variable, right? If you're doubling the random variable, you're quadrupling the variance. Right? But the standard deviation would kind of circle back to that. But we always want to get to standard deviation from variance. We always want to get to standard deviation from variance if we're dealing with discrete random variables. That's important to remember. Always want to get to the standard deviation from the variance. And then lastly, maybe two ideas here, is what if we said, all right, we're gonna get separate checks, but we're gonna pool our discount, right? And say, well, there'd be any difference between getting one bill and doubling. Would there be any difference to what they're proposing there, or doubling the discount? So what we're talking about here is really adding or subtracting random variables, and this is where it gets a little different. This is where it gets a little tricky for people. When we're talking about adding or subtracting random variables, so we're taking couple one's discount and adding it to couple two's discount, what would the expected value be for that sum? Well, just what you think it would be. And it would be the same as doubling it, right? If we're adding or subtracting random variables, the expected value is the sum or difference of those variables, of those expected values. Right? When we're talking about the variance, and this is where it'll take another example. Regardless of whether we are adding or subtracting random variables, we always add variances. We never, ever, ever add, or we never subtract variances. We're always adding variances. We never add or subtract standard deviations. We always want to get to standard deviations from variance, and this is where that idea is really important. So that's why you're always going to want to have the variance available. If it's not given to you, find it. So if you have to do these things like these, adding them together, and this is where we'll get lots of practice in class. I promise you that, right? You're going to want to do that. So we're always adding variance because, right? So we'll talk about what I think is a good example of how that'll help you see it, right? So our expected if we added these values together, we would expect, again, an $11.66 discount, which is the same as doubling it. Here, though, we're going to add the variance. We're going to add the two variances together, 70.306 to 74.306 to 74.306, and we're going to get a smaller variance, and as a result, we're going to get a smaller standard deviation. We are minimizing the variation of what we can be, what we could be seeing, right? Which is kind of the basis of how insurance works. It spreads the risk out amongst so many people, and then there's not nearly as much risk to what they're going to have to pay out. Right? So we're always adding variances, always, and here's why. It's called the cereal box example, right? Variance is a measure of uncertainty, right? Variance is a measure of uncertainty, so we never, regardless of whether we're adding or subtracting, we're never subtracting uncertainty. We're never being more certain. So here's our example, right? Let's just say this box of Honey Nut Cheerios there on the screen holds 16 ounces, right? I'm just making something up here. That's what it says on the side of the box. Is it exactly 16 ounces? Well, no. We'd be shocked if it was exactly 16 ounces. It's going to be somewhere close. There's going to be a range of values, which they're going to say it's going to be within here, but it's going to be pretty close to 16, right? And that bowl holds 6 ounces. So we take our Honey Nut Cheerio box and we have close to 16 ounces, but we're not quite sure. We're close, but we don't know. And we fill close to, but aren't sure of 6 ounces into the bowl. So we've taken an uncertain total and subtracted from it an uncertain amount. It's close, but we don't know. Are we more or less certain about what's in the box now? Well, we're not. We have more uncertainty, right? We have more uncertainty because we didn't, because of all the uncertainty at all the various levels, right? So because it's a measure of uncertainty, we're not sure what it is. That's why we always add variances. They always add, right? And that is once we start talking about a lot of the examples from the text, you'll see how that comes into play, and how you're going to really want to pay attention to what the question is really asking us to do, and what we have to set up in order to get to specifically the standard deviation in the right way, right? And then lastly, and this is another importante grande, when we're dealing with random variables, this is an algebra class, so 3x doesn't necessarily equal x plus x plus x. If you're finding 3x, you're tripling the value of the random variable. So we're doubling the discount like we did in our example at the Quiet Nook restaurant. X plus x means we're adding 3 random variables together. When it comes to the mean, it won't make a difference. However, when it comes to the standard deviation, and by default, it comes to the variance, and then by default, the standard deviation, it will make a difference. So you really want to make sure that if we are dealing with multiple random variables, which is oftentimes what we are going to be dealing with in these problems, make sure you really have got a good sense of, okay, here they're asking us to add together however many of these random variables. We're not making the outcome, we're not making that individual random variable bigger, we're adding a bunch of them together. And again, that will make more sense once we start going through these. So there's a lot there, a lot of important things to remember. I will tell you, this is where it does get a little slippery for people. So you want to make sure when we have the opportunity to practice, you take the opportunity to practice, to make your mistakes in the practice, so it doesn't, so we don't do it when it counts. We're going to have plenty of chance in class to do this, and please let me know if you have any questions. I hope this helped.